In this lecture, we're going to discuss the embedment analysis, or what is keeping the post from actually pulling out of the approach ramp. Now, there's two ways to see this. We can look at it as the post pulling out of the concrete blockout, or we can look at the post and concrete blockout pulling out of the abutment and ramp fill. Now, I think the second case is more likely if failure were to happen. So we're gonna look at the post within the blockout pulling out of the ramp fill. There's a lot going on in this diagram I've created for this lecture. We can see the height of the post above the approach ramp, the height below or the embedment, and the diameter of the blockout in the fill, and the point at which we're analyzing the moment that's created by the live load and the dead load. But note that the code that we'll discuss later talks about the moment at grade. So we're not going to be concerned with recalculating that moment. We'll use the same moment from the post analysis above and the same dead load from the post analysis above, because we're looking at this at grade. The only difference here is before we're looking at the dead load as an axial force centered in the moment as well, centered in that post. So there was no resisting moment from the to resist the live load forces. However, in this case, because we're looking at the blockout overturning or pulling up and out of the approach ramp, we can use the dead load as a resisting moment force. So first, we're going to navigate to the IBC, the International Building Code, Chapter 18, Section 1807, in Equation 18-2, in 1807.3.2.2 for constrained posts gives us the required embedment equation. Now, to discuss these terms, should be S3. Now, to discuss these terms and what they actually mean, sorry about that, we will go into first discussing the moment of the post at the grade, which we previously calculated in the previous section, and we don't need to recalculate here. And more importantly, what S3 is, our allowable bearing pressure. Now, the process of calculating this starts at table 1806.2. where we first take our initial lateral bearing pressure S to be 1,200 pounds per square foot for hard rock. We can multiply that by 2, which is the isolated pull factor from section 1806.3.4. And then we'll multiply that by 40 centimeters in order to get our S3 value that we can plug into the equation above. However, if you do this, you'll find that the required embedment is greater than 40 centimeters, so the check does not work. So we need to go back and use some engineering judgment to reconsider how we are interpreting the code. So 3 things that we can do are first to drop our load to just 200 pounds. We can assume that the distributed load that is going through the fencing mesh and the tie wires and the cables are picked up. Some portion of that is going to be picked up by the cables and picked up by the mesh fence, and it's not all going to go into the overturning of a post over that tributary width of 200 centimeters. So we can, by using some engineering judgment here and also assuming that this guardrail is not going to be used as heavily as what we think the code probably is designing it for, we can drop this to 200 pounds, which is just our impact force. We can also add our resisting moment, like I discussed above. So we can take the moment from the dead load, multiplied by that distance from the center of the post to the edge of the blockout, and add some resisting moment. And we also can assume that the impact force is not being applied at full height. All those 200 pounds aren't hitting the very top of the post. We can assume that everything is coming in from the fencing or the impact is happening close to the top of the post and drop that to 105 centimeters. At this point, we get something that is very close to working. And if you do the math, you can make the final assumption that the cables are picking up some of that load like we assumed before. And we calculate that that's about 7 pounds per cable. So the tension in those cables, because they are routed from the bottom of the approach ramp to where the bridge span begins, we can assume that actually if the guardrail were to start failing under an impact, some of that, or start to pull out under an impact, the tension in the cables is what's keeping it in place. In the next section, we're going to discuss the infill components, which will be the final component of this check. And the infill components include our wire mesh, our tie wire, and our cables. We won't discuss the cables because we already know that these are far stronger in tension than what forces we're going to see from a guardrail.